Okay, great. So yeah, guys, today we are going to finish up chapter 3. I realize we've been talking about sequences for a long time, but I think we should be ready to move on to chapter 4 before we're out of here today. Just to remind you, on Tuesday we were talking about Cauchy sequences, and it's the definition here, of course, is similar to the definition of convergence of sequences. Because you start off with an arbitrary epsilon greater than 0, and you seek to find an n naught in the natural numbers, right? So all of that's kind of par for the course, but such that, and then here's the difference. We have two numbers greater than or equal to n naught. Any two subscripts that are greater than or equal to n naught, those two terms have to be less than epsilon apart, okay? The nice thing about the definition of a Cauchy sequence is you don't have to make a reference to what the limit of the sequence is. Okay, so if the sequence converges, there would always be a limit, and in our definition of convergence, we have that limit appearing in the definition. Well, here you notice that in this condition, the only things that appear are terms of the sequence itself. So there's no mention of a limit to the sequence. We don't have to know what that is to digest the actual definition of a Cauchy sequence. So on the surface of it, that may seem like a weaker notion than a convergent sequence. So Cauchy versus convergent. I want us to think about this a little bit, right? The Cauchy sequences don't make a reference to what the limit of that sequence is. And so in that sense, it seems like a weaker definition. It seems like a weaker definition. And in fact, on Tuesday, we proved pretty easily that a convergent sequence is always Cauchy. That's because the definition of a Cauchy sequence is weaker. So it's easy to prove something that's weaker. However, it turned out, it took a little extra work, but we did prove on Tuesday that actually, although it looks weaker, a Cauchy sequence is the same thing as a convergent sequence, as long as you're viewing the convergence as being in R. Okay, so that I think is a nice observation to make. If you choose a different domain, right? So maybe I should just show you an example. This theorem does not work over other domains, and I did write down one example, I think, on Tuesday. I'm going to write another one down right now. Okay, so theorem 3.12 fails for, let's take Q. Let's take a different domain. Let's imagine we're working in the rationals, and I can give you a very easy counterexample. So what I can do is I can let x1 equal 3, x2 equals 3.1, x3 equals 3.14, x4 equals 3.141. And you can tell what I'm doing is I'm just gradually adding additional digits of pi, 3.14159, and so on. This sequence is a sequence in Q. This is Cauchy in Q. So this xn is Cauchy. It's a Cauchy sequence consisting of a bunch of rational numbers. Anytime you have decimals that stop, then you're talking about a rational number. So these are all rational numbers, right? Basically truncated versions of pi. But however, xn doesn't converge in Q. Because we already know that it does converge to pi. So I'll just say, since xn converges to pi, and pi is not in Q, right? So this is a sequence that if you were only allowing yourself to think about the rational numbers, you would say that this sequence doesn't converge, right? But it's still Cauchy. Okay, it meets the weaker definition of being Cauchy. How come it's Cauchy? It's Cauchy because it actually does converge to some limit, which is pi, And convergent sequences are always Cauchy. This backwards direction is always true. It's just that for Cauchy, we don't have to talk about what the limit of the sequence is. And so that the fact that pi is the limit doesn't come up when you're thinking about it as a Cauchy sequence. So anyway, it's just nice to keep in mind that for real numbers, which is really what this class is about, this is real analysis, right? Cauchy and convergence are in fact equally strong. They are basically equivalent to one another, and we did prove that on Tuesday. Okay. Questions so far about the recap or anything from last time? It's really just wanted to get this theorem back on the board again. Again, why do we spend time talking about Cauchy sequences? If it's just the same thing as a convergent sequence in R, why do that? Again, just to reiterate, the point is that if a sequence is Cauchy, there's no reference to what the limit of the sequence is. Sometimes we don't know what that limit is. Okay, so I'm going to actually do a couple of examples here to kind of drive that idea home a little bit more, if we're all good so far. So far, so good. Okay, let's do another example. What I'm going to do is I'm going to let xn be equal to 1 plus 1/2 plus 1/3 plus ... up to 1 over n. And my claim here, is that xn does not converge. By the way, I should mention that I'm not really planning to spend much time in this class on series as opposed to sequences, but one thing you learn about series, if you might remember from your earlier calculus courses, is that a series converges if and only if its sequence of partial sums converges. And you can actually view this as like a partial sum. You're like taking 1 plus 2 plus 3 and you're stopping at some finite point, right? This is just another way of sort of saying, I will use this notation here briefly, that if we take a summation, n going from 1 to infinity of 1 over n, this is a series. Okay, and what does it mean for this to converge? It would mean that this sequence of partial sums converges, which it doesn't. So therefore, this series fails to converge. You guys probably know this. You've probably seen this before, that if you add up 1 over n, it blows up to infinity. In fact, let's try to show that again. I'm going to maybe prove this here so you can see it fresh right now. But I'm going to claim that this does not actually converge at all. So it's actually pretty easy to do this. So we have x1 is just equal to 1. You can just see that would just be the first term. And then x2 would be, sorry, I have to try to pin this thing here. How do I do that? I think that should be okay. So x2 would be 1 plus 1/2, which I'm going to just write it out like this, 1 plus 1/2, which is 3/2. Okay, and then I'm going to skip over x3, and I'm going to jump up to x4 real quick. x4 is, well, it's obviously 1 plus 1/2 plus 1/3 plus 1/4. But that is actually greater than 2. So you've got 1/3 plus 1/4 adds up to, well, maybe I could let me write it this way. Sorry, I'm just going to do this. I'm going to say that it's greater than 1 plus 1/2 plus 1/4 plus 1/4, which is obviously 2. So I take the 1/3 and I cut it down to 1/4, and then we get 2 out of that. Let's do x8 next. x8 would be, well, it would be all of the first 4 terms again. Okay, so we already know something about that. And then plus 1/5, plus 1/6, plus 1/7, plus 1/8. And guys, if I take each of these, if I take the 1/5, 1/6, 1/7, and I change them all to 1 over 8 instead, I'll get another greater than here. So I'm going to get greater than, the first part is just 2. So I'll put 2 plus 1/8 plus 1/8 plus 1/8, but plus 1/8, and that's adding another half to what I had before. So this is now 5 greater than 5 halves. I'm trying to see a pattern here. So we have a 1, then we had 3 halves, now we have 2, now we have 5 halves. So it's really 1, 1.5, 2, 2.5. So I'm not looking at every one of my xn's, but I'm noticing that the ones that are powers of 2 are kind of growing by 1/2 each time, right? So in fact, if you did x16, I won't write this one all the way out, but you know, you'd have a whole bunch of terms. I could just write this as x8 plus, and then it would be 1/9 plus dot 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 plus 1/16. And again, I can take the x8, it's greater than 5 halves, and I've got 8 copies of something that would be, well, if I replace each of these fractions with 1/16, there's 8 of them, that adds another half to it. So now you have 3, you see. So 5 halves plus 1/2, which is 3. So basically, in general, x sub 2 to the n. So if I want to know what is x1 or x2 or x4 or x8 or x16, is always greater than half of n plus 2. Just kind of check this. So like when n is 3, this says x8 is greater than 5/2. That's what it said here. When n is 4, this would be x16 is greater than 3. Right, and so on. So we have this idea here. But guys, this n plus 2/2 is unbounded. As n gets larger and larger, it gets unbounded. And I'm looking here, guys, at a subsequence. This is a subsequence of the original xn. And if the subsequence is unbounded, then for sure the original sequence is too. And if it's unbounded, it doesn't converge. We know that, right? Convergent sequences are always bounded. So if something is unbounded, it doesn't converge. Let's write some of that down, right? So the sequence x, the subsequence, I should say, x sub 2 to the n is unbounded. Hence, fails to converge. Anything unbounded cannot converge. And if there's a subsequence that doesn't converge, then neither does the whole sequence. So thus, xn doesn't converge either, the entire original sequence. Because if it converged, then we had a theorem, right? That if a sequence converges, then every subsequence converges to that same value. So in this case, by way of contradiction, if xn did converge, then x2 to the n would have to have converged, but it doesn't. So we're in good shape here. Okay. Does that make sense? Now, since it doesn't converge, I should point out, I should also note as just as a remark here, if it doesn't converge, then it's also not Cauchy. Okay, because Cauchy and convergent are basically the same thing. So xn is not Cauchy either. This would be by theorem 3.12. It's not Cauchy either, even though it's not Cauchy, even though if I look at 2 consecutive terms, let's just compare 2 consecutive terms. Let's take the nth term and compare it with the n plus first term. What would this be equal to, by the way? One over. So xn plus 1, we're adding all of these together up through 1 over n plus 1, and then we're subtracting all the ones that are here. Isn't it just 1 over n plus 1? Yeah, and that, my friends, does go to 0. So the 2 adjacent terms are going to 0. If I gave you an epsilon, right? If I gave you an epsilon, we would be able to find an n naught such that the n and n plus first term were less than epsilon. Now, that's not the full strength of this definition though. This definition says, no, it's not good enough just for two adjacent terms to get arbitrarily close to each other. This has to be for all n and m, and n and m could be miles apart, right? So your terms this could be, n could be 1,000 and m could be 1,000,000, something like that, right? And even then, when I subtract xn minus xm, the difference has to be less than epsilon. So I'm just making a point here that it's not good enough. You might have wondered that. It would be a reasonable thing to wonder, oh, so if my sequence is Cauchy and this is true, is that the same thing as just saying that any two adjacent terms are getting as close to less than epsilon as I want for any epsilon? Turns out, no, it's not the case. Okay, so that was just one remark I wanted to make on that example. Everybody okay? Yes, Cozy?
You have to do induction, right?
If I wanted to prove this right here, I would probably formally do it using induction. Yeah, I did not actually take the time to do that, but that would be the way to do it.
Okay.
Yeah, good point. Absolutely true. Okay, as long as I'm on a roll here, am I on a roll? Everybody with
You're
me?
always on a roll down here.
Okay, good. I want to look at a slightly different sequence and talk about it. So let's let xn, one more example here. Xn is going to be this time 1 plus 1/4 plus 1/9 plus 1/16 plus ... plus 1 over n squared. Okay. And my claim this time is that this sequence does converge. Isn't that interesting? So the fractions are going smaller at a much faster clip this time. And it turns out that that is good enough to make this thing converge. So this sequence does converge. And again, I'll put the equivalent series phrasing of that in here. This just means if I do a summation with n going from 1 to infinity of 1 over n squared, that one does converge. Right. Did you guys learn at some point, like, under what circumstances does this series, I'm just thinking back to calculus. Right, if I have the series 1 over n to the p, right, sometimes that blows up to infinity, other times it does converge. And this actually diverges, in other words, it doesn't converge if and only if the p is it's not about odd and even so much, it's just about how big the value is. Obviously, it diverges if n is 1.
It's less than.
Less than 1, yeah, that's basically it. I guess, yeah, p is less than 1, so that's a fact. If p is 2, like it is in the example we're doing right now, then this is gonna not be true. It won't be a divergent sequence, it'll actually converge. That's what I'm gonna show right here. Does that look familiar?
Yeah.
I think they proved that using the root test or something from your math 150B class, second semester calculus. Anyway, how am I gonna show you that this converges? This is kind of clever as well. I thought this was kind of clever. But this one's also pretty nice. So let me just show you how this works. It turns out that xn, we want to write it out. We can write it as 1 plus 1 over 2 times 2 plus 1 over 3 times 3, and so on, 1 over 4 times 4, etc., up to 1 over n times n. So just make my denominators look like that. And I'm now going to make the right-hand side larger by making each of these denominators a little bit smaller. So I'm going to keep the 1 in front, but instead of 1 over 2 times 2, I'm going to replace this with 1 over 1 times 2, which makes the denominator smaller, which makes the fraction bigger. I'm going to do the same idea here. I'm going to replace 3 times 3 with 2 times 3. Then I'm going to replace 4 times 4 with 3 times 4. I'm going to keep going. The last one is going to be 1 over n minus 1 times n. So this is just a clever trick that works really nicely on this problem. And then now we're going to create a little bit of a telescoping sequence here. So I need a little more room here, so I'm gonna come back over here to show you this part. Does everybody agree with that first step though, at least? I've made each denominator smaller. So on the right hand side, the denominators got smaller by replacing part of it with a smaller number, and so the right hand side is a bunch of bigger numbers added together now. Okay, well, what I can do, guys, is I can write this as 1 plus, this time I have an equal sign. I'm gonna take 1 over 1 times 2, isn't that weird? I'm gonna write it as 1 minus a half. So everybody agrees this is 1/2? And so is that. Okay, what's the next one? The next one is 1 over 6. 1 over 6, but I'm gonna write 1 over 6 as 1/2 minus 1/3. So this would be 1 over 2 times 3. Okay, the next term would be 1 over 3 minus 1 over 4, so what is that? That's really 1 over 12, which is the same thing that we have right here. And we just keep going like this all the way to the end. The last one will be 1 over n minus 1 minus 1 over n. And again, if you were to simplify this with a common denominator, you would get 1 over n minus 1 times n, which is the last term here. Okay, now you notice what's gonna happen? Cancel, 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 cancel. Everything's kind of canceling except what does not cancel here. 1 plus 1, 2, and
Minus 1 over n.
minus 1 over n. That's exactly right. Okay, but the point is that that is definitely less than 2. So xn is less than 2. And so what this tells me, guys, is that for all n in the natural numbers, 0 is less than xn is less than 2. And what does that tell you about the sequence? It's bounded, right? Great, so xn is bounded. Is there anything else you could tell me about this sequence? Just the original we've done the hard part, but there's something else about this sequence. The values from x1, I didn't actually calculate any of them, but I could have written down x1 and then x2 and then x3. What would you have noticed about those numbers? It's an infinite sequence, but just the numbers themselves. So x1 would have been equal to 1, x2 would have been equal to 5/4, x3 would have been equal to whatever 1 plus 1/4 plus 1/9 is, and so on. What would you notice about those numbers?
Increasing.
I heard it. Yes, monotone increasing, right? It's actually monotone because each term you're adding another little positive bit to what you had before, right? So like xn is this thing. Xn plus 1 will be all of this plus one more positive term. All of these terms are positive, right? So this is bounded, and clearly xn is monotone increasing. Nice, I'm glad you guys caught that. What do you know about a sequence that's both bounded and monotone? It converges. That's the MCT, the monotone convergence theorem. So by the MCT, xn converges. That was what the claim was. That's what the claim was. So it's bounded by this little algebraic trick that I presented just now, and it's clearly monotone because you're just adding more and more positive numbers with each successive term. So it converges, and I think I mentioned on Tuesday what it converges to. Remember, the MCT does not tell you what it converges to. It just says, yes, it converges. So we don't know what it converges to unless we study Fourier series, and that's a different class. But it turns out, so this is just for your own information, it turns out that it converges to pi squared over 6. So there's a little bit of an interesting connection there with trigonometry. Okay. Well, very good. Any questions on these two examples? That's about as much as I'm gonna do with convergence of series. This is basically what we're talking about, because each of these xn's is like a partial sum of a series. So I did one example that diverged, and now we have one example that converges. Yeah. And they're very similar to each other. So it can be kind of a subtle point. Okay, any questions about Cauchy sequences or either of these kind of interesting examples with series that we just did? Don't hesitate, guys, we're all friends here, all on the same team. If there's questions, I want to help as much as I can. Okay, one last, yes, question.
Just for the conclusion that we came up on the second.
Oh, this over here, this was the previous example.
Yeah, the previous.
Yeah, right.
How did we get the x to the power again?
Well, I was
That just
looking.
a little trick for
I
me.
was looking at x1 and then I did x2 and then I did x3, right? And I kept noticing that it was greater than something. And I just looked for the pattern.
Oh,
I just looked for the pattern, so I just said, oh, I'm noticing that those fractions are all, n plus 2 over 2. I didn't prove it. If I really wanted to prove it, as Nkosi mentioned earlier, I would want to use induction to actually prove this for all n. But I didn't want to distract us with all of that.
Thought it says that if the xn is bounded onto an increasing, then it converges to the supremum.
Well, it does converge to the supremum, but the question is, what is that supremum? Yeah, finding that supremum would not be an easy thing. Turns out it's this. Good point. Good question. Any other questions? So good. Okay, great. Guys, I want to spend just a minute because I don't want to feel guilty about your next homework assignment. I've given you some problems in the next assignment from section 3.7. And so I should say something about it. I actually did talk about this section when we were reviewing for our last exam. This is about limits at infinity. And I won't spend a long time on this, but I'll at least maybe do an example or two. But I introduced this during my review sessions, and I don't want to assume that everybody saw that, so I'm going to present it formally here. Like, in other words, what does it mean for xn to converge to infinity or to minus infinity? Either one. So we're going to make two definitions here for both infinity and for minus infinity. Keep in mind, though, that if a sequence converges to infinity, it's proper to just say that it diverges, right? So this sequence here actually diverges, okay? Fails to converge, right? So that's okay to say that. Infinity is not really a number. So when we say that a sequence converges, normally that means there's a finite number that it's converging to. So this is kind of a little bit of an abuse of language to say that this converges to infinity. But this is pretty standard. So let's get the two definitions down. The first one, xn converging to infinity, is for all alpha greater than 0. So that's just in the same role that epsilon has been. There exists an n naught in the natural numbers such that if n is greater than or equal to n naught, xn should be greater than alpha. So it's kind of nice. We don't need to use any absolute value bars in the definition for this one. It's just a direct inequality here. Xn needs to be greater. So if you give me an alpha, even if you give me 5 trillion as your alpha, then I have to be able to find an n naught such that all of the terms beyond n naught are greater than 5 trillion, right? So that's the idea. For all alpha, we have to be able to successfully find this n naught. Yeah. And for converging to minus infinity, we have almost the same thing. I'm going to use stick with the book's notation here. They use a beta for this one. For all beta less than 0, there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, this time the only difference is xn needs to be less than beta. something like that. Okay, so let me just do one quick example here. Kind of give us a chance to practice with this definition. Let's prove that the sequence n squared minus six n plus one converges to infinity. Let's take something like that. So this is talking about plus infinity, so I'm gonna be using the first definition, the one on the top line here. I've got two definitions running here, guys. Just gonna put them together. So I'm using the top one for the example I'm doing right now. And so if I look at it, what is the first line of my proof going to be? Let alpha greater than 0 be given. Exactly, so it used to be epsilon, now it's alpha. Let alpha greater than 0 be given. Our job is to come up with an n naught. How do you suppose we're gonna do that? What did we normally do in the earlier sections when we started something like this off? I would say let epsilon greater than 0 be given, and then what did I go off and do? Scratch work, exactly. So let's make some scratch work here. I don't think this will take too much. Do a little scratch work on the side for a minute, and what we're hoping to get eventually is that xn is greater than alpha. But of course, xn in this case, xn is just this n squared minus 6n plus 1. We want that to be greater than alpha. Okay, be sure to use logic connectives here. For the most part, I had one of these on the midterm that was mostly very good, but just make sure you're always putting these logical connectives from one step to the next, and make sure the arrows are gonna work in both directions, okay? What I'm hoping to do now is try to solve for n. Now, I could use the quadratic formula, okay, I suppose I could do that. Then I'd have a square root to think about, and the math of that would be, I mean, it'd be okay. But there's really an easier way to do this, which is to just sort of cheat a little bit and say, look, I don't need the plus 1 right now. And I really only need the scratch work to go backwards, right? Because I'm gonna be ultimately starting at the bottom and working back up to this conclusion. So would you guys agree that if n squared minus 6n is already greater than alpha, that then if I add 1 on the left side, it would still be true?
Yeah.
Definitely. So this backwards arrow is okay, but I would not be happy to see that as a biconditional because it doesn't work the other way. But it does work backwards. And I want to make this even easier on myself. This is really, well, here, let me just factor this. This is n times n minus 6 greater than alpha. So that step is totally just reversible, totally factoring it out. And I think it would be true, and I'm going to use only a backward arrow here, that this would be implied by the assumption that n minus 6 was greater than alpha. So if n minus 6 was already greater than alpha, and you took that n minus 6 and multiplied it by n, you would only make it bigger. You would only make it bigger again. So certainly if this was true, then this one would be true. And this now allows me to basically solve for n pretty easily. 6 plus alpha. N is greater than 6 plus alpha. Okay, so a couple of those steps were not reversible. You just have to be a little careful, the arrows that I'm using here, because this is actually the meat of the proof. Because over here, I'm just gonna say retracing the scratch work, right? So this is really where all the hard work is happening, okay? So I go back to my main proof now. Let alpha greater than 0 be given. What am I gonna do next? In the main proof. By the AP, thank you, Brian, Archimedean principle. By the Archimedean principle, there exists an n naught in the natural numbers such that n naught is greater than anything I want it to be greater than, and you always just want to pick whatever you found over in the scratch work, which in this case was 6 plus alpha, right? Okay, so now We just have to check that that N naught satisfies our definition. So let's just check the such that part. So if N is greater than or equal to N naught, we need Xn to be greater than alpha. So let's let N be greater than or equal to N naught. And if N is greater than or equal to N naught, which is in turn greater than 6 plus alpha, that means that N is greater than 6 plus alpha. And so retracing the scratch gives that N squared minus 6N plus 1 converges to infinity. That's right. That is a wrap. It's not all that different, is it, than the proofs of ordinary convergence. In some ways, I like it even more because there's no absolute value bars. Right, these definitions are a little bit cleaner that way. How's that feel to everybody? You guys okay with that?
Yeah.
You want me to do one more? I was gonna do one for the beta, I was gonna do one that's maybe on the homework.
Yeah.
Would that be okay? Okay, let's try it. Let's try one more and see. I hate to steal your fun, but I have so much fun doing this problem. So this one I think is more or less from the homework, except I need to find the problem again. I wrote down the statement here. Okay, so let's do this example. So this is on 3.7. This is problem number 7. There's 2 parts to it. I'm gonna do one of them right now, I think. So it just says, let Xn and Yn be sequences in R plus. So these are going to be positive integers. And assume that Xn over Yn converges to 0. Okay. Then what I would like to prove is that, so prove that if I'm sorry, these should be sequences in R minus. I'm sorry, I realize what I did. I think the one in the homework, I'm just gonna put similar here. It's not identical to the one in the homework. I'm gonna do basically a equivalent one. Prove that if it's Xn, for some reason I didn't write down the statement I wanted here. Yeah, if Xn converges to minus infinity, then Y sub n converges to minus infinity. This should make sense. If all of these numerators are getting huge negative, then the only way that the whole fraction could go to 0 would be if the denominator is also becoming hugely negative. In fact, it has to get negative faster to make this quotient come out to 0. So the one that's in the homework is just R plus, and then this is plus infinity and plus infinity. So all you're gonna have to do is do a quick little sign change on this proof and you'll get it. So we are proving this right here. And that is the second definition. To prove that Y sub n converges to minus infinity, we have to start with a beta less than 0. Let beta less than 0 be given. All right. And well, it's kind of interesting. If there's a beta less than 0 that's already given, and we already know that Xn converges to minus infinity, then there already exists an N naught for the Xn sequence, because we are assuming this, right? So since Xn converges to minus infinity, there already exists an N naught, except I'm not going to call it N naught because it's not going to be the final N naught. I'm going to call it N1 in the natural numbers, such that if N is greater than or equal to N1, Xn is less than beta. So this is just translating that definition over there, but I'm using an N1 instead of an N naught. My goal is to prove that Y sub n is less than beta. Right, that's what I have to prove. I have to prove, because I'm trying to prove this. We need to show. We need to show. So I am proving that given this beta less than 0, that Y sub n is eventually less than beta. Okay, you guys with me? I know that Xn is eventually less than beta, but here's the main point though, guys, you can kind of get the intuition. If Xn over Yn is going to 0, that means the denominator, right, has to be bulkier than the numerator. So they're both negative. These are both, the numerator and denominator are both negative, but the denominator needs to be more negative than the numerator. And so if the numerator is already less than beta, you can imagine that so is the denominator, right? Okay, so let's use that extra assumption there. So let's see if we can get the math to work out. Guys, I don't just want the intuition on these. Sometimes in the homework, I'm seeing people kind of still waving their hands, just kind of like, oh, roughly this is the idea, which is what I just spoke out right now for this problem. But ultimately, we need it to be very rigorous in terms of using the definitions precisely. That's kind of one of the main points of this class. So the intuition is definitely part of it in terms of figuring out how to do it, but then we have to still write it down pretty formally. Okay, so since Xn over Yn converges to 0, we have a definition for that as well. There's going to exist an N2 in the natural numbers such that if n is greater than or equal to N2, then I do need absolute value bars this time, right? The absolute value of Xn over Yn minus what it's converging to, which is 0, is less than, normally we have an epsilon here. I don't have an epsilon on the board here. I do have a beta, but beta is negative and it doesn't really make sense for this to be a beta. The point is this can be any value that we want, right? We are assuming this convergence. So that means if you give me any epsilon greater than 0, I should be able to find this N2. I'm going to choose epsilon to be 1. Just going to do that. Okay, so we do know that. And just to clarify this, we don't really need the minus 0. Also, the absolute value, so this is absolute Xn over absolute Yn less than 1. And remember that the Xn and Yn are both negative. So when you take the absolute value of a negative number, what do you actually end up with? A positive, and you obtain it by just taking the negative of the value itself. So this becomes a negative Xn over a negative Yn less than 1. And this is if and only if, I'm almost out of room here. Let's see if I can finish it. I'm going to drop those minus signs. Xn over Yn less than 1. And then would that be the same as Xn less than Yn?
Yes.
Careful. Careful, careful, careful. You have to do what? Flip the signs. Why? The Yn is what kind of a number? A negative number, right? So you multiply through, basically you're just multiplying through by Y sub n on both sides, but Y sub n is negative. So let's fix this before anybody gets it in their notes wrong. The Yn is negative, so it flips that inequality around, actually. Okay, great. So that is the key to the proof. And now I'm going to find my N naught and hopefully be in good shape. All right. So you guys tell me, what am I going to let N naught equal? Because I've got to find my N naught now. What do we usually make it equal to in this kind of a situation? The max, right? The max of the individual N naught. So this is gonna be the max of N1 and N2, like so. That's what we're claiming is the final N naught that we need. And now let's just let N be greater than or equal to N naught. And we're just gonna check that that works. If N is greater than or equal to N naught, then we know that all of the stuff we've derived is true. This is true, because N is greater than or equal to N1, and this is true. And can you see how we're gonna put it together then? Right, so Xn is less than beta, and Yn is less than Xn. So putting that together, Yn is less than beta. That's what we want. That is exactly what we want. Okay. So the one you're gonna do in the homework is it's epsilon easier than this one because there's no negative numbers. It's all with positive, so you won't have any weird sign flipping or anything like that, but it's gonna be the same kind of thing. So use this if you need to. Try it on your own first, but then if you need to, I've got a very similar example on the board here that you can help, that hopefully will help you with next week's homework. Okay. Any questions here? Sweet. Guys, I don't have anything else for chapter 3. This is actually a very nice take. It's like we're almost halfway through the class. I think let's go ahead and take a 10-minute break. When we come back from the break, we are gonna start a whole new topic. We'll start talking about continuity of functions and limits of functions. So that would be a bit of a different twist. So this is a good time to take 10 minutes and get some fresh air and a break, and then we'll come back. Can I erase over here yet? Okay.
I didn't know he was in his office.
I had
No problem.
the door closed and
Oh, and you were in there?
I was.
That's.
And she didn't know I was in there, but she got there after I went in there.
But I'm usually there so early in the morning to like.
But you went that early today then, cause I didn't get there till.
I got in at like 9. But I
I was
usually
there
get
probably
it-
by about 8:30, and then like I said. I
That's usually what
collapsed.
time I get here is like 8:30. And
Yeah.
so
Oh.
I was like, oh my God, I usually see them walk in at like 10.
Yeah. I'm sorry.
It was
And
fine.
you're
I was just like,
by yourself.
no, I was with Jaden. It was just the two of us. And then I was like, who's coming out of Dr. Hayden's office? It's so random.
That's funny. Is it raining yet?
Yeah.
I heard it, remember that it's raining.
You told me that.
I just tried. I can't call out when there's like paper.
I originally did. It was.
I can still deny.
Not supposed to.
No,
No.
but I already got it.
Okay, so
It
you-
is supposed to be a little windy. I talked to my friend, he's like, no, he says he's done this mountain in worse conditions.
Okay.
I'm gonna trust him on it. Fly all the way up there.
I still feel like the timing is just not right, Dr.
You know, honestly, I don't
Later,
have that
later.
much going on this weekend
Yeah.
though, like, there's no exams, no review sessions, if I wait another week or two. then
Yeah,
I
you're gonna be
expect to
busy.
Busier with school again, so, and I can't wait till spring break, because spring break, I'm probably gonna have plans with my family, so.
Yeah, I understand. I'm
That's
just
the
like,
deal, this is like the best opportunities.
I'm just like, put it off another year. What's the big deal?
Since I've already put it off
We've
4
already
years.
waited all this time.
Yeah.
Can't
For
see.
that's for sure.
I played a soccer game last night.
Did you, in the rain? Ooh, isn't that injury prone?
Yeah, that's what he does. He sleeps. with
You must not have played too rough then, because I would think
So then I
you could slide around.
And usually.
I would think you'd slip on the mud or.
I mean, you got clean.
If he slept
Yeah.
outside, he'd be happy.
It was turf too.
Okay.
Yeah.
That helps, but
Yeah.
still, there you got a lot of lubrication on the ground. Who did you play with?
I played in men's league.
Oh, you're in a league, that's it.
Yeah.
Okay.
Oh, man, I like, since I've been at the California King Blanket, because I am wrapping myself up in that thing.
I have a baby, I have like a throw blanket.
No way, I'm like, give me this thing, I'm gonna cocoon myself in here, leave me alone. Yeah. Yeah, well, we did 3 years. 3 years.
Going back to San Diego tonight? You got your exams done and.
They're not.
That's good.
I'm
You feel okay about it?
I'm like.
No.
I'm still a little tired today, so I.
It's have to be.
It is what it is, kind of thing.
Unfortunately, the ones only offered.
As a whole frame.
Semesters.
Two semesters.
They don't offer it in the summer.
No.
And this is the Wednesday class. When I was. Talked to him a little bit, he's a nice guy. Gives you some advice.
Well, he's my.
Advisor, oh, okay, yeah.
Yeah, let me know what classes to take next and we'll see the better.
Still sounds
Uh-huh.
awful. That still sounds awful.
About as good as you could hope for. Yeah.
I would be leaving class like. Just then.
So I'll be handing out the answers to the next midterm.
Oh, good. Thank you so much.
And it'll be the last 5 minutes.
Okay. And if we share them with anybody, you can't use them,
Then,
right?
then that's not allowed.
That's what I thought. Just Just check.
It's a good thing we got that report on Zoom.
For legal
I might have to
purposes.
remember to turn the camera off before I do it, before the last 5 minutes. Oh, yeah.
Maybe if you wanna do that with studio. It's gotta be able to get ready to buy.
Or more than we didn't say open or to
Both of my stats.
Okay, for masters,
Then she got separated and then I just got waited.
you're waiting. Waiting a little bit. Okay, for next fall.
Yeah, next.
Nice, nice, nice. It'll be here before you know it. That's where I went to grad school. Did you know that?
No.
Yes, I spent 6.5 years of my life living there. So if you have any questions, I will tell you, it's no cheaper than living around here.
Yeah.
Yeah.
I wish I could tell you different. Ay, ay, ay.
Didn't even wanna know.
There's a-
I know.
just never moved.
No, yeah, it's crazy, isn't it?
But it was like,
it.
that's a phone that was. Things are similar.
It's not. It's 'cause
Yeah.
How do people figure this out in writing? Most times it's a ground experiment.
I don't.
No, you don't.
All right, everybody, I think it's been about 10 minutes or so. Hopefully there's a couple people, hopefully they're on their way back shortly. What I want to do for the second half of our class today is talk about something completely different. We've been talking in all of chapter 3 about sequences, and we can think of a sequence as, you know, and we did define it this way, a function from the positive integers to the real numbers. So our notation was x1, x2, x3, x4, but that was really inputs and outputs. 1 was the input, x1 was the output, 2 is an input, x2 is the output. When you're talking about functions that go from the natural numbers to the real numbers, it's not as important to have this notion of continuity, the idea of a continuous function, because after all, the inputs are kind of discrete to begin with. Right, 1, 2, 3, 4, those whole numbers are separated from each other in a discrete set. But what we're gonna do now, guys, in chapter 4 is we're gonna start studying functions that actually go from R to R. All right, so instead of just sequences, which is what we were doing in chapter 3, now we're gonna be looking at functions from R to R. And one of the most important concepts in preparing for calculus is the idea of a continuous function. Guys, if we start thinking about some of the big theorems in calculus, the mean value theorem, you have to have a continuous function. The intermediate value theorem, you have to have a continuous function. Even the fundamental theorem of calculus itself, which is kind of the big prize at the end of a class like this, you've got to have a continuous function in your hands. So this is a very powerful assumption. And the good news is that a lot of functions are continuous, right? Polynomials are continuous, rational functions are continuous as long as the denominator is not zero. Sine and cosine, all these very familiar functions from calculus, they are continuous. So we're gonna get a lot of mileage out of this material, which we're gonna be studying continuous functions for, because the results we're gonna do require continuous functions, and most of the functions that we study have this beautiful property, okay? Now, I am going to cover this chapter in a little bit of the wrong order, okay? So John's sitting here looking at page 1 of chapter 4. We are gonna actually jump into section 4.3 first. And that's because that's where the hard work really is. I wanted to do the hard work first, which is just understanding limits of functions, because somehow we're gonna use that then to define what continuity means. So we're gonna actually start, we start with limits of functions. And so this is in actually section 4.3. So I am gonna be kind of a little out of order here. 4.3 first, and then we'll go back from there. Let me just kind of recall for you the intuition that you might have. Again, intuition is not going to be proof worthy in a class like this, but just so you have the idea, like what does it mean to talk about the limit of f of x as x approaches c? Okay, this could be equal to some value L, right? And sort of what it means is, I'm gonna put this in quotes because again, it's just intuition. It's nothing formal yet. It's intuition, but it just means that as x gets close to c, but x is not actually equal to c. You might remember when you take the limit of f of x as x approaches c, we specifically do not allow x to equal c. So I've added that here as part of the description that I'm writing. The value of f of x gets close to L. So I'll just kind of put all of that in quotes. This is just the rough idea about what a limit of a function is, okay? And we could even, draw a picture as well. We could have an x-axis. There's some point C here, and maybe we have a function f of x, and I'm just gonna draw out a little open circle here right at C and maybe plot the point somewhere else. Because it doesn't matter what f of c itself is, right? The main thing that matters is just what's happening to f of x as x gets close to c. And there might be some y value of L that the function is approaching as x approaches c. All right, so that's kind of the way you wanna think about this. Maybe you even remember it a little bit this way in your freshman calculus courses. This is about as far as they often will go. Just kind of try to give people the intuition behind it. And then they look at graphs and do basic algebra to calculate these limits, okay? But I am going to give you a much more formal treatment of this now. And so we're gonna start with the definition here. Now we're gonna get serious, okay? That was just kind of the introduction over there, the intuition behind this idea. But what we're gonna do here is we're going to let D be a subset of the real numbers. The D is going to stand for domain. So I wanna imagine that D is a domain inside of R. F is going to be a function from D to R. So I know that over here I said that the function is going to go from R to R, but we could have some restricted domain. For example, if we were talking about the natural log function, you wouldn't have all possible real numbers as inputs. You could only input positive numbers. So this domain might not be the entire real number line. It's just some subset of it. I'm going to let L be an element of R sharp. So I'm actually going to allow the limit value to be plus or minus infinity. Maybe the graph has an asymptote right at C. And so you could have a plus or minus infinity, so that's why I've allowed for R sharp. And I also need one more thing, I have to have the C value. Notice that actually C doesn't even have to be in the domain, to be honest with you. I don't even have to have a value for f of C, we can still talk about the limit. So the C is not required to be an element of D, but there is one thing we need to require about it. C is an element of the accumulation points of the domain. I have to be able to get arbitrarily close to C by using points in the domain. So just to remind you again, the accumulation points, these are all points that, so if you take any neighborhood around C, you've got to have infinitely many points of D in it. Right? That was the group work that we did on Tuesday. So you've got to have, this C cannot be an isolated point out in the middle of nowhere, right? It's got to have points of the domain all around it. So that's the setup of this definition. So in this case, we say that the limit as x approaches C of f of x equals L. Or sometimes we will use arrows. I'll just put this as another notation. You could just write f of x with an arrow to L, and then you'd have to put another expression under the arrow, which is that x approaches C. So sometimes I'll do that. I personally prefer to write it more formally here using the lim word. And so what is the definition? What does it mean to say that the limit of f of x as x approaches C is equal to L? It just means if for every neighborhood, now we're gonna get the words that we need here. For every neighborhood V of L. Okay, so let me pause for just a moment. I'm going to draw you a neighborhood of L. So a neighborhood would be just going up or down by epsilon from the L value. So this might be epsilon this way and epsilon this way. So for every horizontal strip that I make around L, this is what V is. So V is this neighborhood of L. For every such horizontal strip, there exists a neighborhood U of C. And let me, well, I'll go back to the picture and draw it in a second. But for every neighborhood of L, there has to exist a neighborhood of C such that if X is an element of U, and it also needs to be in the domain. We have to be able to take f of x. So I'll say intersect. So if x is in the intersection of U and D, and x does not equal C. Remember, we don't care what actually happens when x is equal to C. Then f of x is an element of V. Whew, that's a tongue twister. That's a tongue twister. So for every blue strip that we can draw around L, right? I can make a neighborhood of C down here. I'm gonna go ahead and try and draw it for you. I'll draw this one in red. This is U. And we can think of that U as creating kind of a vertical strip centered on C, such that for every single X value that is within this strip, except possibly C itself. So notice that f of C is not in the blue strip, right? But f of everything else, this is supposed to be perfectly centered around that point. Everything else lands in the blue strip. So all of those f of x's that are heavily shaded by my marker here, they all have to end up in the blue strip. Does this intuition make sense? The one point that we don't care about is f of c itself, which could be outside of the blue strip. That does not change or affect the limit value at all. Right, so there you go, that's the definition. Now, if somebody comes along and decides to challenge you a little bit harder with a narrower, blue strip here, that would be a tighter neighborhood, a smaller neighborhood, you might have to adjust your red neighborhood, right? You might have to shrink that down as well, but this is a game that we play, it's like a two-player game. One person controls the blue strip, one person controls the red strip. The person with the blue strip passes that out to the red player. The red player has to come up with a strip such that all of the f of x values land within the blue strip. And if the red player can always do that, no matter what blue strip was given, then we say this. Okay? Good enough? I don't like all this words. I'm gonna rephrase this now using, epsilons, stuff like that. Let's rephrase right here. Let's just get right into it. Let's rephrase this definition in a handy way that we will be using pretty much all the time. So here's what we're going to say, guys. The limit of f of x as x approaches c is equal to L if and only if and only if, so it says here for every neighborhood V of L, well, that's going to be governed by the epsilon, right? So I'm just going to say for all epsilon greater than 0. Okay, and then based on that epsilon, there exists a delta. I should have included that in my picture here, guys. This red strip has a little bit of a radius as well, and this radius is called delta. Delta, so let's add that in the note over here. There exists a delta greater than 0 such that if, now here we go, 0 is less than absolute x minus c is less than delta. And I do need this 0 here because 0 less than, x is not required to be equal to c. So if x was equal to c, this would be 0, and I'm not trying to apply this to x equals c. That's the reason for that 0 on that side. And I should say x is in D. So the x's that we're going to consider are only the ones that are actually in the domain. Then the distance between f of x and L, which is measured with the absolute value of f of x minus L, that should be less than epsilon. That's the definition. So again, just to make a quick little note here, this 0 less than thing is just, I'll just say here, since x is not going to ever be equal to c when we're looking at this definition. Okay. So this is rephrasing it using epsilons and deltas. Just to give you an idea how important this theorem is, I taught this class a few years ago. We had a pretty active math club. It might have been close to 10 years ago. We had a pretty active math club, and they were trying to come up with a t-shirt. And I had been teaching 350, and I said, well, you guys need to memorize the definition or whatever. And they were trying to come up with a t-shirt design, and they can and did make the t-shirt to have, it said Cal State Fullerton Math Club, and they put that definition on the front of the shirt. And so I think their plan was to come to the exam with that shirt on. And see how it would go. But anyway, I had to sort of tell them that they couldn't wear the shirt that day. Yeah. Anyway, there is one little snafu here, guys, that you might, I don't know if you've noticed this yet. I said that L could be infinity or minus infinity. It's in R sharp. Well, it obviously doesn't make sense to be subtracting infinity or minus infinity from a number. So this actually needs to be tweaked a little bit to say when L is real. So I'm not going to rephrase the sort of plus infinity, minus infinity case yet, although we could. But generally, this definition is going to be used in the case when the limit is a real number. And as long as L is real, then f of x minus L will make sense. Okay. You might also be wondering, what does a neighborhood of infinity look like anyway? I know what a neighborhood of C looks like. It looks like a little interval going from x minus delta to x plus delta. But what does a neighborhood of infinity look like? Well, it turns out that, so when, maybe I should add this as a little, I think I have this here as a little comment, just maybe back over here, guys, just make a little remark. This is not a big deal, but just, I don't want anybody to get confused by this later. You know, if L is equal to infinity, because that is allowed, then what is your neighborhood of infinity going to look like? Well, it turns out a neighborhood of infinity is just an open interval going from some value A off all the way to infinity. So it's like an array of the real number line. And similarly, if L was minus infinity, then the neighborhoods of minus infinity would just look like intervals of the form minus infinity, comma, B. Just to dot my i's and cross my t's a little bit on what that would mean. We will mostly focus on limits that are actually real. Especially here at the beginning, that's mostly what we're gonna work with. Okay, any questions about the definition or how I've rephrased it so far? Does it seem reasonable? Let's just do a quick example if you guys are good then, with just using this definition. I'm going to define f from R to R by f of x equals, and I'm going to make this a piecewise definition. It's going to equal 2x plus 3 if x does not equal 2. And we're gonna make it equal to 2025 if x does equal 2. So this is my function. It's basically a line. 2x plus 3 is just a line, but we've displaced one point from that line and plotted it up, you know, at the value of 2025. And here's what I want to do. I would like to show that the limit as x approaches 2 of f of x is equal to, does everybody know what they think it'll be equal to?
225.
It's not 2025, because remember, we don't care what happens at x equals 2. It's gonna equal 7, exactly. If I plug in 2 up here, 2 times 2 plus 3 is 7. That's what we would claim. It's going to be 7. I mean, if you draw the graph, here's x equals 2. This is technically 7 right here. At this value, this will be 7. And you just have a line, basically. And then 2025 is way up here. Sorry, this is not to scale by far. But you get the idea. Yeah. Okay, so that's basically what you have. Now, if we already knew that 2x plus 3 was continuous, then we would know that this is the answer directly by plugging in 2 into the f of x. But I have not covered sections 4.1 and 4.2 yet, which are where we would learn that. I'm doing the hard work first, which is this section, where we're doing the epsilon delta definition of limits, and then we're gonna go back and define what a continuous function is. But I'm not assuming that we know anything about continuity right now. Okay, so we're just gonna do this directly. Let's get the proof going. And I'm gonna use the rephrased definition here, which means what's the first sentence of my proof going to be? Let epsilon greater than 0 be given. Now, normally at this point is where I ask you how to find the n naught. That's what we've been doing for oh so long. But we don't have an n naught anymore. Now what we're trying to come up with is a delta. Okay, so we're changing the game a little bit. The goal is to find a delta greater than 0 such that blah, blah, blah. And so how do you suppose I'm gonna do that? Say it again. Scratch work. Exactly. We're gonna do this just like we did for sequences. I'm gonna come over here on the side and I'm going to make a little scratch page. Right, and I'm gonna see if in the scratch work I can come up with the conclusion. The thing that we want, of course, is the absolute value of f of x minus 7 is less than epsilon. That's what I'm aiming for. Remember, L is 7 here, right? So that's what we want. So let's just see if we can do some steps. And again, just like before, I want us to use these logical arrows to connect these steps together. I do want to have in mind that while I'm doing this, x is not going to be equal to 2. Right? And since x is not going to be equal to 2, I can pretty much take f of x as being 2x plus 3 for the purposes of this calculation. So I'm going to go ahead and feed that in right here, 2x plus 3, right, and then minus 7 less than epsilon. Okay, so again, I'm thinking ahead that I'm ultimately going to be assuming that 0 is less than x minus 2. So x will not be equal to 2 in any of the application of this scratch work. Okay, let's see. This is pretty easy, isn't it? I can take 2x, that's really 2x minus 4. I'm going to pull out the 2 from that. So it's 2 times the absolute value of x minus 2 less than epsilon. And what you're trying to get out of this, guys, is you're trying to get something about absolute x minus c, right? Because ultimately this is going to be the assumption. And the delta is determined through this part of the definition, right? So I'm going to figure out what the delta is according to x minus c. So let's solve for it here. It's actually just epsilon over 2. Okay, and everything here was totally reversible up and down. And so that is going to be the answer. We are going to come back to our main proof now. And we are going to let delta equal epsilon over 2. Make sure that you've already put your rubber stamp sentence down here first, because it doesn't make sense to just see the epsilon showing up from out of the blue right here. So you start by establishing the epsilon, then you come up with the delta. And just like we had to do in the last chapter, once we found our n naught, we still had to verify it, right? We had to verify, basically, in this case, it's going to be this condition right here. So let's do that. Let's just check this. So now let's assume that 0 is less than absolute x minus 2 is less than delta. Well, then that means that I'll just drop the 2 part, and the 0 part, and I'll just replace delta with epsilon over 2. That means that absolute x minus 2 is less than epsilon over 2, and now we can just retrace the scratch work. Okay, so just like we were doing in the last chapter, we can now just say we're going to be retracing from scratch to get absolute value of f of x minus 7 less than epsilon. And so there you would have the proof. Okay. Any questions on that? Seems okay. Does the 2025 ever come into it? You see it written down over there anywhere? Not at all. That's why every time I teach the class, I can just change it to whatever year it is. Doesn't make any difference. It's going to be the same exact proof. Let me tweak this example slightly to make it a little harder, because that one was pretty much no surprises, right? Let's do one more slightly harder example here. Let's define f from R to R by f of x equals, and again, I'm going to do this piecewise, 2 pieces. So I'm going to take 2x plus 3 again, but this time that is going to be if X does not equal 2 or 1.9. And then I will let it equal 2025 otherwise. So if X equals 2 or 1.9, then we'll use 2025. Okay. And I'm going to do the same exact thing. I'm going to show again that the limit of f of x as x approaches 2 is still going to be equal to 7. It's the same exact conclusion. But the problem this time is that there is a value of x other than just c, where the f of x is going haywire. It's going way off the charts, and I'm not gonna be able to get, f of x minus 7 to be less than epsilon. If f of x is 2025, I'm pretty sure this is not gonna be less than epsilon, most likely. So, there are some bad x, well, there is a bad x value that is close to c being 2 here. So, I'm wondering if anybody has an idea. So for the proof, I'm gonna start off the same. Let epsilon greater than 0 be given. I don't wanna write out all the scratch work again, but I'm wondering if anybody thinks they could just find a delta for me. Or give me an idea about how to come up with a delta that would help me to get around this little issue that, gosh, if I plug 1.9 into the function, I'm gonna get 2025. Is there an easy way that we can kind of make that problem go away? So now we've got 2 holes in the graph. These values are way up here somewhere. Here's 7. This hole we don't have to worry about for sure, because c equals 2 is excluded from even being considered just straight from the definition. This hole makes me nervous. If my delta was, out here like this, then there'd be an x value inside of that neighborhood where f of x is miles from epsilon, right? Or miles away from 7. Is there something we could do to kind of deal with this point that's over here, 1.9?
Will you be able to make your neighborhood small enough to exclude that?
How small would it need to be to exclude it? How far apart are these points?
Point.
Just 0.1. If my delta was less than 0.1, and then that 1.9 would be outside of that neighborhood anyway, right? Now, if epsilon is 0.00005 or something like that, then by the time I divide by 2, for sure, the 1.9 will be outside of it. But if my epsilon is like 500, some big number like that, then half of that is 250. That would be too big of a delta. So the way we do this, guys, very simple. We're just gonna take a min. Remember in the last chapter, it was always a max. This chapter, it's always gonna be a min. We're gonna take a min of 0.1 and the epsilon over 2 that we had already derived. I won't rewrite the scratch work again. It's literally the same scratch work, that same epsilon over 2 from before. But if that happens to be more than 0.1, I'll just shrink it down so that it is 0.1, like so. So if 0 is less than absolute x minus 2 is less than delta, then we already know that x does not equal 2 and x will not equal 1.9. So I won't have to worry about either of those 2 points. And so then, so the above proof still works. That's really the idea. The above proof is still going to work in that case, because you've excluded the 2 points that were making that argument problematic. That scratch work still works in reverse. Okay? Does that make some sense? Because after all, delta is still, it's less than or equal to epsilon over two. It might still be epsilon over two, but if it's not, it's less than or equal to epsilon over two. And so then, assuming this assumption, this would be still true here, right? And so then you could still just use the same scratch word. So we don't have to write it all out again. Okay, perfect. Questions on that? And if there were maybe finitely many points where there was an issue, you would just take the minimum of all of the 0.1 comes from the difference between 1.9 and 2. If you had several other points also, you would just take the one that was closest to 2. That distance would be the thing that would go inside of here as your for your minimum value for the delta. Yeah. So you can imagine ways to extend this to even more complicated examples. I won't bore you with all of that now. Let's do another quick example here. This time I'm going to let C be an arbitrary real number. So the C is sort of the limit point. And we're going to let it be any point. And then I'm going to let f of x equal x. So I'm just going to take this function here and prove that the limit of f of x as x approaches c. Any ideas what that's going to be equal to? It's really the limit of x as x approaches c, which would be c, exactly. So let's just do this one. This is kind of a generic one. I don't have a specific number in here, but this is actually really quite easy. So for the proof, again, I'm going to let epsilon greater than 0 be given. I'll come over here and give myself some scratch space. Certainly not going to need very much, but we'll just have a little scratch space here to help us with this. So the scratch work should look like, f of x minus c less than epsilon. That's ultimately what we want. And in this case, f of x is just x. And look at that. It basically immediately gives you the x minus c that you're looking for in the definition. So what's your delta going to be? Same as epsilon, exactly. Let delta equal epsilon. We just take delta equal to epsilon, and then we just have to check that that works. So let's assume that 0 is less than absolute x minus c is less than delta. So I always start off with just this inequality on this side, and then I'm going to try to prove this side. Okay, but that's just automatically true. This is automatically true because delta is the same as epsilon. And so we are basically done. You're basically done. So absolute f of x minus c is less than epsilon. So this one is like super easy. Super, super, super easy. So far, so good. I want to do another one. This next one's a little harder. So far, all of these functions, these f of x's, they've all been linear functions. Did anybody ever get asked to do one of these delta epsilon proofs before?
Yeah.
You have done them maybe even in Calc 1, they sometimes, well, I'm glad to hear that because I was worried they'd taken that all the way out of the curriculum. I'm glad that they still do that. Well, let me give you one that you probably wouldn't have done in Calc 1. This one's a little harder. Let's show that the limit as x approaches -5 of 2x squared plus 3x minus 6 is equal to 29. Okay. You can kind of tell where the 29 is coming from. If you just plug in -5 into that quadratic function, you'll get 29. So it's pretty reasonable. Again, this is a polynomial. Polynomials are always continuous. So once we know about continuity, we'd be able to just state that as a direct statement without having to do any epsilon delta proof. But we're still getting our feet wet with this idea of limits of functions. So we actually need to do this one kind of from scratch. So I'm gonna let epsilon greater than 0 be given again. And then I'm gonna come over to my scratch work, and the scratch work is gonna be kind of an important part of this one, so let's make sure you give yourself enough room to write the scratch work this time. This one's got a little bit of meat to it. As always, the ultimate conclusion is going to be absolute f of x minus, in this case, 29 is less than epsilon. 29 is the limit value. And then let's just start with the first step. I just plug in what f of x is. So that's 2x squared plus 3x minus 6 and then minus 29 less than epsilon. And I can now simplify that a little bit. 2x squared plus 3x minus 35 less than epsilon. So I have a minus 35 on that. And remember, what am I trying to get? I want to get the x minus c. Now, what is c? C is -5. So I'm trying to get x plus 5 in that scratch work. It should show up somewhere in the scratch work. Does anybody see how it's going to show up? -5 needs to show up in the scratch work.
So it's -7.
You factored it? Yeah, this factors. Okay, great. I was hoping maybe we get this thing factored. It looks to me like it is going to be absolute of, what did you say, 2x? 2x minus 7 times the quantity x plus 5. Okay, and that's also an absolute value of ours less than epsilon. Okay, yeah, so that factors, and that's just algebra. There's nothing wrong with that. But ultimately, we want to isolate this x minus c part. So technically, what I would need to do now is I would need to say, well, that means absolute of x plus 5 is less than epsilon over absolute of 2x minus 7. Okay. So would I be able to let this be equal to delta? You know, the problem is delta is supposed to be a constant, right? Delta is a fixed number, and now we have solved for this x minus c, and we've gotten something with x in it. This is the first time that this has happened. So unfortunately, we are not allowed to have this as our delta. Now, what we can do, and what we are going to do, is we're going to pick what I like to call a preliminary delta, which will give us at least some interval of x values that would be in play. I mean, as of right now, x could be pretty much anything, although I will point out, x had better not equal 7/2. Or we have a dividing by 0 issue. So what I want to do is I want to make sure that my delta is small enough to avoid 7/2. Now 7/2 isn't very close to -5, should be all right. But what we're going to do is we're just going to imagine, we're just going to impose, delta to be less than 1 to begin with. And this is still in the scratch work. This is still in the scratch work. I'm going to impose that value. Now, does it have to be less than 1? No, you could have chosen 2 or 3 or 4. Just don't make it so big that 7/2 is within delta of -5. Okay, but let's just do that. If delta is less than 1, then how far away from -5 can x actually get? Well, it would get at most 1 unit away. And how far would that allow me to go? Well, to 1 unit on either side of -5 would be the interval from -6 to -4, right? So this imposes, so then what we could say is that -6 is less than x is less than -4. Okay, so guys, I am not saying that my delta is equal to 1 yet. I'm not even choosing a delta yet. When I'm ready to choose a delta, I'm going to come back to the proof. What I'm saying is we can, if we want, make sure that our delta is less than some value. And by doing that, our x's will already be limited here, okay? Now, if we plug in -6 into here, Okay, I might not write every word of this down, so just kind of follow along with me. If I plug in -6 here, do you agree that I'll have epsilon over 19? If I plug in -4 into here, do you agree that I'll have epsilon over 15? So I either have epsilon over 19 or I have epsilon over 15 or something in between. Right? I always wanna imagine the worst case scenario or the smallest, the minimum of the deltas, which would be the epsilon over 19. The bigger denominator makes that fraction smaller. And if x minus c is less than epsilon over 19, then of course it's also less than epsilon over 15. So I'm gonna do that, right? So in this interval, I'm still in the scratch, guys. In this interval, absolute x plus 5 will be limited to being less than epsilon over. Actually, sorry, let's do it this way. In this interval, sorry, I meant to say absolute 2x minus 7, right, is less than 19. And so I'm going to do an arrow now in the scratch work here that is a backwards arrow only, which is going to be absolute x plus 5 less than epsilon over 19. If this is true, then if I make my denominator a little bit smaller, that would make the fraction bigger. So that would mean that x plus 5 would be big, even more, it would definitely still be less than a bigger fraction. So this is making it as small as I could by choosing the 19 rather than the 15. You see what I mean? Okay, so now I'm gonna come back to the main proof. And I'm going to let delta equal, everybody know what I'm gonna choose? The minimum, exactly, the minimum of 1 and epsilon over 19. Now, if you had chosen your preliminary delta to be 2. So if you had started off here with 2, well, then your x would be ranging from -7 to -3. And when you evaluate that in here, you would end up getting something like if I put in negatives, I would get an epsilon over 21. That would not be wrong. So you could have said let delta equal the minimum of 2 comma epsilon over 21, and that would also have been fine. So I'm not saying you have to choose 1 here, right? It's just a nice number. That's why I'm choosing it. And of course, it's staying far, far away from 7 over 2, which is also good. Okay, so we've got our delta here, and now I'm going to assume that 0 is less than absolute x plus 5 is less than delta. So I'm just now I'm checking it. I'm going back to the definition. I'm going to check that that delta works. The fact that 0 is less than absolute x plus 5 is less than delta means that 0 is obviously therefore less than absolute x plus 5 is less than 1, because delta is at most 1. And so we're going to start off by pointing out that x really does live between -6 and -4. So we're in the situation that we can now apply the scratch work for. Okay, and so thus absolute of 2x minus 7 is less than 19. We wrote that over there in the scratch as well. And so since 0 is less than absolute x plus 5 is less than epsilon over 19. Now, where's that coming from? That's just going back again to, that's just going back to this again, right? 0 is less than absolute x plus 5, it's less than delta, but delta is less than epsilon over 19, because we're taking a min here. See, so I have to use both of these. I have to use this one to get the limitation on the x values right away, and then the rest of the scratch work applies to the other one. You actually have to use them both in the middle of this proof. But since 0 is less than absolute x plus 5 is less than epsilon over 19, then well, then we can retrace the scratch work. Because then you're basically saying that this is true, which implies this one, this one, this one, this one, and all the way along. So then retrace the scratch work to get absolute f of x minus 29 less than epsilon. And that's basically it. That is basically it. Well, Lila, you don't look too happy. Are you okay? Oh, okay. Sorry, just making sure. Does anybody have any questions on that? Let me prove one last thing, guys. It's a quick one. I know I don't have a lot of time, but I have enough time to do this. This is quick. I just want to prove that a limit has to be unique. And we did that for sequences. And so we're just going to do that here as well. So this is actually a corollary as stated in the book 4.1. Last result for this week, guys. Last result for the week. Let's just prove that if the limit as x approaches c of f of x exists. We haven't really talked about situations where it doesn't exist yet. But if it exists, then it is unique. This one can be proven in a very short proof. So I just would like to show this to you quickly here. Then it is unique. If there is a limit, it is unique. No surprise. I like proving things that are already intuitively kind of clear. How do you suppose I'll prove this? Kind of by way of contradiction, yeah, suppose that there are two limits, right? So by way of contradiction, suppose that the limit as x approaches c of f of x is equal to L1 and the limit as x approaches c of f of x is also equal to L2. And let's imagine that they're different. Let's imagine that L1 is less than L2, just to assume one is bigger than the other. Suppose they're not the same. By way of contradiction, this is what we're doing. I'm assuming the limit exists, which means there is a limit value to which we can apply this definition. So for all epsilon, there will be a delta such that blah, blah, blah. So what I'm going to do actually is make an epsilon for you. I'm going to make an epsilon, which is going to literally be the difference of those two L values all over 2. So I'm going to take L2 minus L1 and divide it by 2. That's obviously positive in this situation. And so that is a valid choice of epsilon. And so what we can say then is, then there exists, well, there's actually going to be two different deltas. One for this part and one for this part, okay? So there exists a delta 1 greater than 0 such that if 0 is less than x minus c is less than delta 1, then absolute f of x minus L1 is less than epsilon. And there also exists a delta 2 greater than 0 such that if 0 is less than absolute x minus c is less than delta 2, then again, absolute f of x minus L2 will be less than epsilon. And I'm just about ready to give you a contradiction already. I just need to choose or make a final delta now. And that's just going to be the minimum of these two deltas. So you've kind of hopefully already gotten the idea that in this chapter, whenever we have multiple deltas, we always take the minimum of those, right? And if 0 is less than absolute x minus c is less than delta, which is this minimum of these two deltas, then both of these are true. Right? So then. And both of these together are going to be a contradiction. Absolute f of x minus L1 is less than epsilon. And absolute value of f of x minus L2 is less than epsilon. I'm just going to, I know I'm going a little faster, I'm running out of time, but just another minute, we'll be done. Just gonna add them together. On the right side, I got epsilon plus epsilon. That's 2 epsilon. On the left side, I have absolute f of x minus L1 plus absolute f of x minus L2. Like that. And well, first of all, on the right side, 2 epsilon, by definition, that is just L2 minus L1. Go back to how we defined epsilon here. So 2 epsilon is just L2 minus L1. And on this side, my friends, on this side, I can use my triangle inequality. And I can basically, oh gosh, I need more room. Let me put it over here so I have plenty of room to show it to you. I basically do the triangle inequality where I put it all inside of a single absolute value. So I'm gonna switch the sign of the second one and write it as L2 minus f of x. So this is f of x here. The point being it cancels. And you just get, what do you actually have there? You just have L2 minus L1 is less than L2 minus L1. That's a contradiction. Contradiction. And always takes a minute longer than I think it will. But we are done. That is the proof. So it is not possible to have 2 different limits for the same function as x approaches c. What do you guys think? Any questions? All right, if not, we're gonna call it a day. Don't forget, if you want to talk to me in person, try to do it today, or else you're gonna have to wait till Tuesday. I'll be back on Tuesday around noon. But I'll have some Zoom hours on Sunday and Monday from up in Washington. If you want to talk to me about the homework in the meantime. Okay, thanks, guys. I wish you a great weekend.